Hi everyone. In this video, we're going to cover several options for leveraging pre-trained models that you can use on your own data sets. We're going to focus on a technique called fine-tuning, which offers the most flexibility, but we're also going to talk about other options as well, and we'll see that leveraging pre-trained models is especially helpful when you don't have access to a large amount of data to train your model on or your computing resources are limited. Hi there, and welcome to LearnOpenCV. Using pre-trained models out of the box is an excellent choice if you have a broad range of content that encompasses the classes in ImageNet. But there are other ways to leverage pre-trained models to repurpose them for custom data sets. In this video, we're going to focus on a technique referred to as fine-tuning with a coding implementation in which we use the VGG16 network for a classification task. However, all the concepts that we're going to cover here are not specific to any particular model or task. In this example, we'll be utilizing a modified version of the German traffic sign recognition benchmark dataset, which contains 43 classes of German traffic signs. The original dataset is pretty large, comprising over 50,000 images in total across its train and test sets. However, to showcase the effectiveness of fine-tuning on smaller data sets, we've extracted a portion of the original data set which contains just 40 samples per class. And we'll further split those up into 28 samples for training and 12 samples for validation. And again, that's the number of samples that we're going to use to represent each class. So this is a pretty small data set, but to evaluate how well the model generalizes once we've trained it, we'll use the original test set, which contains over 12,000 samples. Before we dive into the coding implementation for fine-tuning, it's worth summarizing the various options when working with pre-trained models. We've already seen some examples for how you can use pre-trained models out of the box, which requires no training, which is indicated in the first row in the table. But we also show 3 additional cases that can be used when you have a custom data set that you'd like to repurpose a model for. These options include training the model from scratch, transfer learning, and fine-tuning. It's important to note that in each of these scenarios, a new classifier must be defined that's consistent with the custom data set. In other words, the pre-trained model's classifier, which is tailored for ImageNet, cannot be repurposed for a new data set, but rather we'll need to redefine the classifier portion of the network to repurpose it for a new task. So we're going to talk a little bit more about each of these cases just to set the stage, and then we'll dive into the coding implementation for fine-tuning. But just starting with the first option, training a model from scratch. If you need to customize a model for a new data set, one possibility is to load the model and train it from scratch. When training from scratch, the entire model is initialized with random weights and training is conducted from the ground up, and also with the new classifier as we mentioned above. Training a model from scratch typically requires a considerable amount of data and computational resources, although that varies depending on the size of the model. While better options are available, we did train the VGG16 model from scratch on this limited data set to provide a baseline performance so that when we train the model for fine-tuning, we'll have something to compare it to. We didn't make any effort to tune hyperparameters, but we did include a dropout layer in the classifier, which is necessary for mitigating the effects of overfitting that we would expect on such a small data set. So we're going to revisit these plots later on in the video and compare them to the fine-tuning results. But if you just take a look at the plots, you can see that even though we did add a dropout layer, the plots do indicate that the model is still overfitting, as the validation loss significantly exceeds the training loss. So it's challenging for the model to acquire sufficient knowledge on such a small data set, form well on unseen data, for example, on the validation data set. And then one thing that's worth mentioning here is that the initial loss should be somewhat close to random chance, given that we haven't trained the model yet. So, for example, with categorical cross entropy, the loss is the negative log of the probability of the correct class. So initially, we would expect that the probability of the correct class would be roughly 1 over 43, which is the number of classes. And therefore, we would expect the initial value for the loss to be somewhat close to this value of 3.76, which we've also indicated in the first plot. And so this can just be a nice sanity check when you start working with a model in a new data set. The next option that we're going to take a look at is called transfer learning. And in this case, we load the pre-trained model's feature extractor and define a new classifier for the data set. So the only portion of the model that we load from the Keras application's API is the model's convolutional base preloaded with ImageNet weights. And then we'll need to define our own classifier, which is consistent with the data set, meaning that the number of outputs is equal to the number of classes. So in the figure, we show a newly defined classifier with a single layer and 128 nodes, and an output layer with 43 nodes. Other than the size of the output layer, which must be 43 for this particular data set, the number of layers in the classifier and the number of nodes per layer is a design choice and doesn't have any relationship to the original classifier of the pre-trained model. Notice that also the new classifier is loaded with random initial weights, and when we train the model, we only allow the weights in the classifier to be updated. So the rationale behind this approach is that the pre-trained ImageNet feature extractor has learned valuable features for detecting various object types, and we presume that these features are general enough to apply to other data sets. So therefore, we only need to retrain the classifier portion of the network to learn a new mapping from features to classes. And this results in a faster, more efficient training process. However, sometimes retraining the classifier isn't enough, and that's where fine-tuning can be very beneficial and a more flexible alternative to transfer learning. So let's take a look at that next. Fine-tuning is quite similar to transfer learning in that we still load the pre-trained convolutional base with ImageNet weights and define a new classifier initialized with random weights. But instead of locking down the feature extractor completely, we freeze the initial layers of the convolutional base so they're not trainable, but we allow the last few layers to be trained further. So the portion of the model that undergoes further training are the last few layers of the convolutional base, as well as the newly defined classifier. The underlying idea is that the initial layers in the feature extractor capture very generic low-level features such as edges and corners and arcs that are essential building blocks necessary to support many classification tasks. The subsequent layers in the feature extractor then build upon these lower level features to learn more complex representations that are more closely related to the content that's specific to our custom data set. So fine tuning is a powerful technique because it allows us to adjust the pre-trained model's existing feature extractor to be more relevant to the specific use case without starting from scratch. It's important to emphasize that all the layers in the feature extractor are initialized with ImageNet weights, and then during training, the weights in the last few layers of the feature extractor are refined to learn an improved set of features that are specific to the dataset. On the other hand, the weights in the classifier are initialized to small random values as they need to learn a new mapping from features to classes. So the term fine-tuning really comes from the fact that we start with ImageNet weights in the feature extractor and then fine-tune them to improve the model's performance on our custom data set. Remember that we can always train a model from scratch, but doing so on a very small data set will most likely limit the model's ability to really learn and generalize well. But with fine-tuning, we can leverage many features from ImageNet, which enables us to start in a state that would otherwise not have been possible. So now that we have a general idea of where we're headed, we're going to focus on the fine-tuning implementation, which also implicitly covers transfer learning, but with a small amount of extra code to demonstrate how to control which layers in the feature extractor are trainable. We're also going to spend a little bit of time preparing the test data set, which is in a different format than the training and validation data sets, and therefore represents an excellent opportunity to explore a couple of different techniques that can be used to manage image data that's organized differently on the file system. So let's go ahead and get started, and we'll begin with the downloading of the custom data set that we've prepared for this example. We've already discussed some of the details associated with this data set, but one thing that's worth mentioning is that the original data set is comprised of images that came from video sequences. So many of the images in the training data set, for example, are from adjacent frames within a video sequence. And therefore, in order to create a smaller version of the data set, we needed to sample the original data set at every nth image in order to maintain the diversity within the data set. So each of the classes in this smaller version of the data set, which contain 40 samples, 28 for train and 12 for validation, still have the same diversity as the original data set, but just a smaller amount of images. In this next section, we're using the Python data classes module to several data and training configuration parameters that we're going to use further below in the notebook. In the data configuration section, we specify the number of classes, the shape of the input data expected by VGG16, as well as the path names to each of the data sets. If you take a look at the file system, you'll see that there's a train, validation, and test folder, and the train and validation folders contain subfolders for each class, which is a typical format for specifying training and validation data. However, you'll notice that the test folder simply contains unlabeled images, and the labels for those images are located in a separate CSV file. And so we'll talk further below in the notebook about how to load and parse that information, which is going to be different than how we treat the training and validation data. And then for the training configuration parameters listed here, these are the same values that we used when we trained the model from scratch. And we didn't make any effort really to fine tune these. We just picked a reasonable set of parameters based on some experience and then locked those down for both cases so that when we execute the fine tuning model, we can compare that to training from scratch and have an apples to apples comparison for those differences. So with that, let's go ahead and continue on to create training and validation dataset objects in the next section below. In a previous video earlier in this series, we used the load method in Keras to load images and labels from the CFAR10 dataset into NumPy arrays. Loading data into NumPy arrays is fine for small datasets, and since the CFAR10 dataset is available in Keras, we had the added convenience of being able to use the load method to load the dataset directly into NumPy arrays. However, in general, it's better to create what's called a dataset object, which is a more efficient way to handle data, especially when you're working with larger data sets. For this particular example, we don't necessarily require it, but it's a good time to introduce a utility in Keras called Image Dataset from Directory, which is very convenient for creating an image dataset. The expected file structure for this utility is shown here, where the images for each class are contained in a separate class subfolder within the top-level folder for the dataset. By default, the class names in the dataset are inferred from the class folder names. The function only has one required argument, which is the top-level folder, for example, the train folder. And then there are several optional arguments which can be used to configure the dataset further. Many of these options have reasonable defaults, but it's important to take a look at the API to better understand what those values are. For example, even though the image size is considered an optional argument, the default image size is 256 by 256. So unless you have a model that requires that specific size, you'll need to set it as we did here, since VGG16 requires 224 by 224. So we've used this utility now to create both a training dataset and a validation dataset. And remember that the default behavior is to infer the class names from the folder names that are on the file system. And if we scroll down here a bit further, you can see that printing out the class names list from the training data set. And notice that it's in alphabetical order, not numerical order. And so this is due to the fact that the class names are all digits. So this doesn't really create a problem for the train and validation data sets, but it does have an implication for how we create the test data set so that the test data set has a consistent set of labels. And so we'll come back to this further below in the notebook when we create the test data set. And just a reminder that this is not something you typically need to worry about, but with this particular data set, since the class folders were named with digits, we end up in this situation, and it's something that we need to take care of when we create the test data set. So now that we've created both of these data set objects, before we proceed with processing those, it's always a good idea to take a look at the data set. And so in this next code cell below, we're going to print out some of the samples from the training data set. And so we're going to start by retrieving the class names. And notice that we can do that by accessing the class names attribute from the training data set. And then we can use the following for loop to access the first batch of data in the training data set. And we do that with the take method. And we're going to give it an argument of 1, which means we're going to ask for the first batch of data. And that returns for us an image batch and a labels batch. And so the image batch will contain a batch of images, and the labels batch will contain the corresponding labels for those images. And then for each image, we're going to set up a plotting grid and display each of the images and their associated labels. And as you can see in this first batch of data, there's quite a wide range of image quality. For example, several images are severely underexposed. Those would be the dark ones. And there's also some blurriness and even some images that look like the resolution is pretty low. So this just gives you an idea of the diversity within the data set. So now at this point, we're ready to continue on and create a test data set. As we mentioned earlier, the test data for this data set is organized differently than the training and validation data. So the test data is all located in a single folder called test, and there's no structure to that folder to indicate what the classes are. So we have one test folder and it has over 12,000 images in it. And class labels for that data set are located in a separate file called test CSV. And here you can see a sample of that file, and you can see that the seventh column of that file contains the class IDs for each image in the test data set. And so there's no convenient utility that we can use to assemble all this in a test data set object. So we're going to have to write some custom code that strings all this together. But at a high level, we can summarize the steps as retrieving the class labels from the provided CSV file and storing those in memory as a Python list. Likewise, we'll need to build a list of image file paths in memory as a Python list, and then we can combine those two lists to create a tfdata.dataset object. And then finally, we'll use the dataset objects map method to apply some convenience functions to load and pre-process the images in the dataset. And we're going to get started by using a Pandas data frame to help us read the class IDs from the test file into memory. And we'll store those IDs in a variable called ground truth IDs, which is a Python list. And notice that there's 12,630 IDs that we read from the file. And here we're printing out the first 10. And you can confirm that these IDs match the first 10 IDs in the file. So that's just a sanity check. And recall that when we created the training and validation datasets up above, that the class names for those datasets are now in alphabetical order, not numerical order. And here we've printed those class names out again just for easy reference. So in order to make a consistent set of labels for the test data set, we're going to need to create a mapping from the original class IDs to these new IDs. And so that's what the focus of this next section is. And before we walk through a little bit of code that's required to create this mapping, we did want to point out, and we included a note in the documentation here, that there is an alternative solution to this. Image dataset from directory does have an optional argument called class names, and we can therefore supply a specific list of class names in a specific order to that utility, and it'll maintain that list in the datasets. So for example, if we had supplied a list of class names to that utility in numeric order, then there would be no need to create a mapping because the order of the class names in the training and validation dataset would match the class names in the test dataset. And so while that's certainly more straightforward, we thought it was important to show this alternative solution just to underscore what the issue is. And as an exercise, you might want to experiment with this by commenting out the code that we're about to go through and implement the training and validation data sets by using a class names list. So let's go ahead and continue on and describe how we create this mapping. In the first code cell, we're creating a dictionary that maps the ground truth IDs from the test file to the IDs in the class names list in the training and validation data sets. So, for example, we're printing out the contents of the dictionary. And so now we're going to use this dictionary to map all the IDs from the test data set to a new set of IDs that are consistent with the training and validation data set. So that's what this next code cell does. It uses the dictionary we just created to map all of the ground truth IDs in the test file to the associated labels in the training and validation data sets. And here you can see that we're printing out the first 10 IDs from the test file and their new mapping to the IDs in the class names list in the training and validation data set. And just for reference, we're also printing out class names list from the training and validation data sets. So before we continue on, let's just summarize where we're at this point. The whole goal here is to create a test data set that contains a set of test images and the corresponding labels for those images. Normally, we would read the IDs from the test file and store them in a Python list as we've done here. But in this case, we had to take a small detour to create a different mapping from test IDs to the IDs in the training and validation data set. But apart from that, the process is still the same, and we end up with a list of label IDs for each of the images in the test data set. So in the next section, we're now going to deal with the images. So let's take a look at that next. So we're going to start by creating a list of image paths. And to do that, we're going to use the glob utility as shown here. Then further below, we're printing out the first 5 paths from the list just to confirm that we've created that properly. And then in the next section, we're going to combine the image paths and the label IDs into a test dataset object. Notice that we haven't read in the images yet, but we're going to do that in just a minute. So we use a function called from tensor slices. I think the naming of this is a little bit confusing, but this function will take these two lists, the image paths and the label IDs, and construct for us a test dataset object. Further below, we're going to create some convenience functions that we're going to apply to those path names to load the images from the file system into the test data set. And we've got 3 function definitions here. I'd like to start with the middle one, which is called load and process image. Notice that it takes a single argument, which is a path name to an image, and then we call read file to load that image into memory as a byte string and store that in a variable called image. And then we pass the image to the preprocess image function, which is now defined above. And the preprocess image function takes in an image as a byte string, and then we convert that to an unsigned 8-bit image representation using decode PNG. And then we finally resize the image in memory to size required by the model, which in this case is 224 by 224. And then that function returns the resized and decoded image. And then further below here, there's another function called load and preprocess from path label. And this takes 2 arguments, which is the path name to the image and also the ground truth label. All this function does is it's just really a wrapper to the load and preprocess image function we just defined above. Now in the next code cell, we can use the map method from the test dataset object to apply these functions to the dataset. And so this returns for us a test data set that contains both the pre-processed images and the associated ground truth labels. And then additionally, we're also going to set the batch size of the data set as shown in the next line of code. So just like we did before with the training data set, we can display some of the images from the test data set, and that's shown in the next code cell below. Just like the training data set, the test data set certainly has a wide range in the quality of the images. Several are underexposed, and there's some that are blurry or a lower resolution. So now that we've configured our data sets, we're ready to go ahead and instantiate our model. And as shown here, we have the interface to the VGG16 model as documented in the Keras Applications API and shows several of the input arguments and their default values. And we're going to use this to instantiate just the convolutional base preloaded with ImageNet weights because we're going to want to define our own classifier further below. And so drawing your attention to the code cell here, we're going to begin by specifying the input shape, which is 224 by 224 by 3. And then we're going to instantiate just the convolutional base of the model preloaded with ImageNet weights. And the way that we do that is we specify include top to be false, which means we're not going to include the classifier since we're going to define our own classifier further below. And then for the weights, we're going to specify those to be the ImageNet weights. So now that we've loaded the convolutional base with ImageNet weights, we need to further configure the model for fine tuning. So recall that this means that we'd like to freeze the initial layers in the convolutional base and only train further or fine tune the last few layers. And in this example, we're going to fine tune the last 8 layers in the convolutional base. And the way that we can configure all this is by making use of the model's trainable attribute. So there's a couple of different ways that we can do this, but in this example here, we're setting all of the layers in the convolutional base to be trainable on the first line in the code cell below. And then we're going to loop over the initial layers and freeze them by setting trainable attribute for each of those layers to false. And then when we print out the model summary below, you can see that the first several layers have been frozen or locked down so that they're not trainable, and only the last 8 remain trainable. And so now when we take a look at the total number of trainable parameters, you can see that number has decreased relative to the number of trainable parameters in the convolutional base before we configured it for fine tuning. So now we're at the point where we're ready to construct the entire model. And we first start with specifying the input shape to the model. And then the very next layer that we're going to add is a pre-processing layer in which we call the built-in pre-process input function for this model. Remember that we need to do that since we've preloaded the model with ImageNet weights. We then add the convolutional base that we configured above, and now it's time to add the classifier. So first we flatten the output of the convolutional base, and then we add one dense layer with 128 nodes with a ReLU activation function, and then we also add a dropout layer. So as we mentioned earlier, we're free to define and configure the classifier however we want. It just needs to have the right number of outputs for the data set, which in this case is 43. And we've simply decided to have one dense layer here, but there's nothing to prevent you from adding another layer or changing the number of nodes in each layer. However, this is the same configuration that we use when we train the model from scratch. And so for consistency and comparison purposes, we're using the same classifier. And then finally, we set the number of outputs to be the number of classes with a softmax activation function. And then the entire model is assembled by using the model class in Keras, in which we supply both the inputs and the outputs. So constructing the model in this way uses the Keras functional API. And recall from a previous video, when we coded a model from scratch, we use what's known as a sequential API. So the syntax is a little bit different, and there's a little bit more flexibility when using the functional API, but we just wanted to demonstrate both methods in this Getting Started series just for reference. And then the last line of code is printing out the model summary. So let's go ahead and continue on to compiling and training the model. We've already seen how to compile and train a model in a previous video, but there's a couple of things we wanted to point out here that might help clear up some confusion as you study this material further. So when working with classification models, you have the option for how to specify the label encoding as either integer encoding or one-hot encoded vectors. And depending on which method you use to encode the labels, you need to choose the appropriate loss function. So there's 2 loss functions that are used for categorical cross entropy. One is referred to as sparse categorical cross entropy, and the other one is categorical cross entropy. When your labels are integer encoded, the appropriate loss function to use is sparse categorical cross entropy. However, if you use one-hot encoded labels, then you should be using categorical cross entropy. So that's the first thing we wanted to point out. The next thing is that there's this input argument to the loss functions called from logits. And that's defaulted to false, so we don't need to specifically specify it here, but it's always good to be explicit. And the way that this is used is that if you have a softmax activation function included in your model for the output layer, then you should set from logits equal to false. But if you don't have a softmax activation function in your model, then you would set from logits equal to true, and under the hood, Keras will implement a softmax function. You'll notice that there is some discussion in the documentation and also on several discussion forums about the differences between these two methods. For example, there's some evidence that under certain conditions, using from logits equal to true is slightly more efficient. But this is more of an advanced topic, and we just wanted to make you aware of this so that when you dig into this further, you won't be surprised by some of these nuances. For training the model, we're going to specify the trained data set, the number of epochs, and then explicitly the validation data set. If you didn't have a validation data set, then alternatively, you could use the validation split argument to the fit method to split the training data set into train and validation components, as we did in a previous video. So next, let's go ahead and take a look at the training results. As you can see in the plots, both the training and validation loss decrease fairly rapidly, and correspondingly, the accuracies for both training and validation increase rapidly. I noticed that halfway through training, the training accuracy pretty much reaches 100%, which is a good sign that the model is able to learn from the data. Also, notice that the validation accuracy pretty quickly gets to above 90% early on in training and then steadily increases. And by the end of training, looks to be about 96 or 97%. So it's pretty impressive that the model is able to achieve these accuracies on such a small data set. Keep in mind that there's other techniques available, such as data augmentation, that could improve the accuracy further. Overall, these results are encouraging and indicate that the model has learned to generalize fairly well on unseen data. And then finally, just for comparison, let's take a look at the difference between fine-tuning the model and training the model from scratch. As you can see in the plots, training from scratch takes quite a bit longer for the model to ramp up, which makes sense since we're starting from random weights and not initializing the model with ImageNet weights. But notice also that the validation accuracy doesn't get past 80% even after 100 epochs of training, compared to about 97% for the fine-tuned model. So this further highlights the advantage of fine-tuning the model when you have such a small data set. And it's also worth mentioning that while data augmentation would improve the performance of both models, the fine-tuned model would train more efficiently and very likely achieve a higher potential performance compared to training the model from scratch. So next, let's continue on to the last section of the notebook where we're going to evaluate the fine-tuned model. For that purpose, we can use the model's evaluate method to evaluate the model on both the validation data set and the test data set. We already have the validation plot above, but if we want to know what that validation accuracy is at the end of training, we can just pass the validation data set to the evaluate method. And as you can see here, the accuracy is just below 97%. Likewise, we can evaluate the test data set. And remember that the test data set has over 12,000 images in it. So this is going to be a really good test on data that hasn't been seen before by the model. And you can see here that the accuracy is also right around 97%. And so this is just confirmation that the trained model generalizes well to the unseen test data. And then further below here, we're going to visualize a few predictions from the model on both the validation and test data sets. And for that purpose, we have a convenience function here called display predictions. And this is going to loop over two batches of images and call the model's predict method to obtain the predictions for each image. And then above each image, we're going to display the ground truth label as well as the predicted label. And if there's a misclassification, then that title will be printed in red so we can identify the misclassifications. So let's go ahead and scroll down and take a look at the predictions from the validation data set. Here you can see that most of these are correct, but if you take a close look, you'll notice that there's two misclassifications. And that's to be expected since the accuracy is about 97% and we have 64 samples. And it's interesting to note that two misclassifications are associated with signs where the prediction and the ground truth are actually the same shape. So this is an indication that the model was on the right track but didn't quite get the right answer. And so next, let's take a look at some of the predictions from the test data set. And in this case, very similar situation. This time we have four misclassifications, and this just goes to show that the model has generalized well to the test data set. So the validation accuracy and the test accuracy were very consistent, and we're seeing that now in these sample predictions. Obviously, there's over 12,000 images in the test data set, so we're not going to be able to visually inspect every one of those, but it's always a good idea to inspect a small sample of the images just to confirm the performance and also to get a feel for are there any peculiarities in the results. In this case, there were not, and it looks like the model is generalizing well. So that concludes our discussion for this video, and we did cover quite a bit of material. We started with several use cases for how to leverage pre-trained models, which includes using pre-trained models out of the box for classification on ImageNet classes. We also covered how to load a model from the Keras Applications API and redefine the classifier to repurpose the model for a different data set. And then we covered transfer learning at a conceptual level and then fine tuning in detail. So we hope this gets you excited about how you can use pre trained models and leverage them for your own applications on your own data sets. We hope you found this video useful. And if so, please like and share the video and subscribe to our channel to get more content on computer vision, deep learning, and AI.